rather than doing a Q&A, ask the audience, I'm just going to very quickly type down. Remember, the postulates are on your first page, the front page, the inside page. All things are made of small things called atoms. They're indivisible, they're too small to be seen, they're in constant motion, colliding inelastically with their neighbours. We don't care about the fourth dot point about the size of the forces. So for this first one, we're going to say that heat is transferred into the balloon. We're going to ignore via which process? And the particles gain kinetic energy. Now it's transferred, which is where the energy stays in its same form. So you've got energy transformation and energy transfer. It's kinetic energy to kinetic energy, so it's an energy transfer. Okay, please get that written down. Now this is where I was discussing or talking yesterday about the explanation questions are where the boys seem to struggle. You're great with your calculations, but they're not so good with the explaining. All right, now one of these, a simple question like this might be worth, come in. Simple question like this might be worth 4 or 5 marks. So get that written down and you're going to be trying to hit all of these dot points. Amelia? That's all yours. I've got an email draft to get into. I'll get your email address at the end of the lesson, okay? And it's got all the links to the lessons. You can catch up if you need to. Heat transferred into the balloon. As temperature is a measure of, and this is where you have to remember that that whole statement. If I could spell particles in a substance now, that's so far nothing new. Internal energy has increased because the heat is transferred into them. We haven't changed the state, we've changed the kinetic energy of the particles. They're now jiggling with a higher temperature. Aiden? Can we check our surfaces, please, gentlemen? Check that you don't have Aiden's. So really it's going to be, how do we search this? How do we do this? Well, is it? Alright, so Matthew, where's yours? Aiden, do you know where Matthew's is? Matthew Sisson? No. No? Do you want to go to IT and find where yours is? Play music on laptops? Alright, sorry Sisson.
Thank you, sir.
Now, no worries. Here's, again, you may be asked in questions to describe certain phenomena using the kinetic theory. There's going to be only a few different types of phenomena: thermal expansion and contraction, increasing in pressure, increasing in temperature, but they can all be explained with the kinetic theory. We'll then say that they collide, or the particles, we'll say they collide with their neighbouring particles and the walls of the container with more momentum Okay, well in fact we could even get one more dot point here. We're now up to 3, hence the volume expands. Okay, so you take a balloon, you throw it into hot water, you would see the volume of the balloon start to expand. Now, heat, they sometimes describe it as the flow of heat because back in the 1700s they thought that heat was a fluid that filled substances. They called it caloric. which was this weird fluid that was responsible for transferring energy. And it kind of sort of just flowed in between all of the particles in the substance. And some phenomena could be explained by this caloric theory. For example, if you got a piece of wood and you set fire to it, you saw the flames flowing out. And they would, well, that's the caloric leaking out. Makes sense. Another observation that explained that the caloric theory explained was if you had a cup of hot water and a cup of cold water, the hot water has more caloric. And when you pour the hot into the cold, the caloric, in quotation marks, mixes nice and evenly. So the idea of mixing mixtures, hot and cold, could be explained. But then, I believe it was James Prescott Joule, who was a British engineer. He was designing engines and motors, and they noticed that when they were boring a cannon, so you get a big lump of cast iron, and you basically drill the hole that the cannonball is going to be placed in, that as long as some mechanical input was present and there was a pressure applied to that metal, you would always have a huge amount of heat being released. Okay? You never ran out of caloric. For as long as you could turn that thing, people might be getting tired, you know, turning the wheel or the pulleys or whatever. For as long as you could enter mechanical energy, you would be getting heat out. So that the caloric theory could not be explained. And that's when they started to develop the idea of work and energy, which is the ability to do work. Sort of you get stuck in this definition loop where energy and work explain each other. But before they managed to do that, people had started making measurements. They had started to measure heat in units of calories. And it still sticks today. We have measurements of calories in our food. That is a vestigial unit. It was based on a theory that was silly. And now we have a conversion that 1 calorie is 4.180 joules. Okay, so once we figured out what energy really was, we could figure out the conversion. I'm babbling on, and we're going to run out of time because we've got heaps of work to do. Let's just skip that bottom one, and let's keep babbling. The reason I was talking about all this junk is because I wanted to say that this was directional. Heat can flow into an object, and all of that happens. But you can reverse it. You can play the tape backwards. And so you could, if the balloon was then placed in the freezer or cold water, you could take all of those dot points and just reverse the verbs. So heat is removed from the balloon. The particles lose kinetic energy. As blah, 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 their velocities decrease. They collide with their neighbour with less force. Momentum. Impart less force. Move closer together. And hence occupy less volume. Hence the volume decreases. Done. You've just, flip a coin as to which question I could ask and put in a test. It's going one way or the other. Okay? Same with this. Instead of volume, you're talking about how close the particles are. They move slightly further apart. So you get expansion in metals and contraction in metals. Okay? This one's talking about equilibrium, which we may have brought a definition to. As the cooking tray boys, you can leave if you aren't following. we will continue to build on this when we do the laws of thermodynamics, talk about thermal equilibrium. But you'll notice while you're writing that, gents, I'm going to probably, I shouldn't have just gone ... but you need to write the definition. I'm going to highlight a couple of those terms. Okay, so we remember from yesterday at Astra, we said, you do have to learn laws and definitions, but obviously this is now using those definitions correctly to explain phenomena. So this is sort of putting concepts into context, which is what I was babbling on about in the chapel yesterday. Okay. I hope, because I'm going to go now into drawing mode, that it's going to do this nicely. Did it? Yes? No? All right. Finish writing? Can I just check what's on the next page? Temperature scales. Okay, cool. Oh no, I've left my pen. Can I borrow someone's pen? Yes. Please don't let me steal it off you, because I will. Thief. All right. I hope you've got that written down. If you have some room, I'd like you to draw very quick. Uh-oh. No. Keep drawing. I'll be back in 1 minute.
Yeah, like I said, it's not a big button on the side. No, it's bookshop. How much they cost? 95.
Alright. Thermometers, right? How do they work? Well, if you know the kinetic theory, you should be able to explain it. So, I'm just going to quickly scribble. Or maybe I was in eraser mode. That's probably why. Here's my thermometer. Where are the rest of my pens? That's weird. And if you were a glass blower in the 1700s, you were a pretty cool dude. Because it was a very good skill to be able to produce this, and scientists wanted to use you. I probably put my capillary too high. However, we're about to get into temperature scales. But first, with your thermometers, they are very delicate. The reason they are very delicate is the bulb at the bottom is quite thin. It is supposed to be thin so that heat can easily and quickly be transferred into the thermometer if you're measuring something hot, or out of the thermometer if you're measuring something cold. Where you place your big nuggety meat hooks needs to be thick. So, for example, how does my thumb look when I'm holding a thermometer? I know, right? Okay. When you hold your thermometer, I had to quickly. I should be teaching that, I reckon. When you hold your thermometer, you do not want any heat coming from your fingers because you're not measuring the temperature of your fingers. And so the glass around the capillary, and we will label thermometers later, needs to be quite thick to reduce the rate at which heat flows into the thermometer if your fingers happen to be hotter than the thermometer. Okay? So, when we measure stuff with these glass thermometers, if you see the capillary rising up the tube, you are visualizing energy being transferred into the thermometer. When you see the capillary falling down the tube, you are visually seeing energy being removed from the thermometer. When the capillary is stationary, you are measuring a thermal equilibrium. That is saying that the temperature of this alcohol is the same temperature as the outside environment, and so there is no net transfer in or out. The movement of the capillary we can explain with the kinetic theory. So let's go in. Remember, we could just as well play it in reverse. As heat enters the bowl, the alcohol gains kinetic energy. As temperature is a measure of blah, 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 their velocities increase. They impart more momentum to their neighbours. They exert more force to their neighbours and hence move further apart. They occupy more volume. Now, our poor little alcohol needs to occupy more volume. It cannot go left, it cannot go right, it cannot go forwards, it cannot go backwards. The only way is up. And so the alcohol rises up the capillary. Okay? That is how thermometers work, at least in glass thermometers. Alcohol in glass thermometers. Okay? It's a lot. Once you start thinking about how something simple like a thermometer works, let's get into Anders Celsius. He was a Swedish astronomer. And he proposed the Celsius scale, which is pretty good, and we still use it. Now, it's also known as a centigrade scale, because he thought that we would make 100 even divisions from one point to another. He needed two endpoints that were quite reliable, and I think we all know them. Shout them out. No, don't, at nothing. No. Okay. So, here's what he did. He was able to easily obtain the double point of water. So he made a thermometer and he allowed the thermometer to get to thermal equilibrium with the beaker, which we call 0 degrees, freezing point. It's very easy to make the double point. The double point is where you have two states existing at once. That's quite easy. You get a cup of water, you dump in some ice, and eventually the temperature of the water will drop. Eventually it gets down to 0 degrees. When it's at 0 degrees, it is at the same temperature as the ice. And if they're at the same temperature, they are at thermal equilibrium, where there is no net transfer of heat. So that's very easy. You get an ice slurry or an ice bath, they will happily stay that way, providing energy isn't removed. So you can very readily get 0 degrees at standard atmospheric pressure. Then you get the other double point. Let's go to the other end. Let's take our water, heat it up, so that it is now bubbling with steam. So down here, Bunsen burner. Okay. Same deal. This is the other double point between liquid and gas. All right. So what at standard atmosphere, once the water gets hot enough, the vapor pressure is now greater than the atmospheric pressure, and it can break free and rise up and be released as steam. So in that boiling water, you have water at 100 degrees, you have steam at 100 degrees. And so literally what he did is he marked the 0, he marked the 100, and he put 100 divisions, equal divisions between the two. So you had to be a very precise glass blower that could produce a long glass thermometer with a capillary on the inside of uniform diameter. Because have a think, if your capillary bulged and narrowed, how would that affect the volumetric expansion of that? You wouldn't be able to measure it linearly. So it had to be perfectly blown. Okay? Don't ask me how they made it, but they were very, very crafty people. I don't know. I'm sure there would be ways to calibrate your thermometers. You could bring, if you're the finest glass blower in your town or country, you could bring your thermometer to the annual international thermometer competition and have, I don't know. Good question. Here's the problem. Water has impurities in it, and that can affect the melting and boiling points. There can be dissolved salts, there can be dissolved gases, there can be bits of dirt and dust and bacteria, and that will affect how we do it. Also, the pressure can affect the temperature at which particles can go from a liquid to a gas. Okay? When it's low pressure, I want you to imagine 1 atmosphere is what we're under right now. That's a lot of force pushing down on the surface of your water. And in order to escape that, you have to be jiggling at such a rate that you can break free from that top surface tension. If you start to remove that pressure, you can escape with less kinetic energy. So literally, at the top of Mount Everest, water can boil, and does boil, at around 70 to 80 degrees. Okay? If you have a pressure cooker at home where you clamp the lids down, it will not boil till about 120 to 130 degrees based on the pressure. Okay? So when you have a pressure cooker at home, you can get higher temperatures in your pressure cooker, which can make your meat more tender. I don't know. So it was later amended. Delish. These are the 2 points. The triple point of VSMO. Well, actually, it's basically just pure water. And absolute zero. Now, the triple point. I used to have all of my different colours up here and my stylus seems to have changed. Triple point of water is 0.01 degrees Celsius at 0.006 atmospheres. I'll explain why they changed it in just a moment, and absolute zero is known to be minus 273.15 degrees Celsius. The reason being is that they are physical constants. They will never change. No matter where you are in the universe, if you have H2O, those temperatures will never change. Right. Now I have a video loaded up of the triple point, so get that written down because I'm about to change. No, what? VSMO. It means very specially purified water. Very specially purified. Essentially, gentlemen, it's very difficult, rude, disrespectful, annoying, distracting, me trying to teach when I can hear 5 people having conversations. Shush. Now, this is a very interesting graph showing the properties of water. Right now, we've got pressure along the y-axis, and as we go along the x, we go along temperature. So basically, here we are solid, and then eventually at 0 degrees, we go from ice to water. Then, for 100 degrees of Celsius, we get to this point where beyond which we are vapor or gas. Okay? But if we were to change the pressure, as I said, if we dropped the pressure down a little bit, like I said to Mount Everest, I can't draw on this, Mount Everest might have a lower pressure due to its altitude, and so water would boil at around 70. Okay? Look what happens to the freezing point. It also increases. The 2 double points have come closer together. At lower pressures, the range that water exists as a liquid is less than 100. Now let's keep going lower and lower and lower. If we keep dropping the pressure, our 2 double points, solid and liquid and gas, are getting closer and closer and closer together. And at just the right pressure, the two double points meet, and that is called the triple point. That is the pressure and temperature at which your matter can exist in all three states. You can have a container with gas, liquid, and solid existing all at once. You can do that with water, but you've got to get down to 0.006. You need to get nearly a complete vacuum, which is difficult and time-consuming. You can do it with any other substance. So, here is the triple point of an alcohol, butyl alcohol. And hopefully, shall I drop it? It is down to... So please, just note if you can. Helps if I press play, yes? No, I just paused it again and I stopped it. Alright, so what you don't see at the top is it's attached to a vacuum which is pumping out all of the air. You can now see an ice crystal or an alcohol crystal forming. And then suddenly steam or vapour bubbling around in the liquid. At the same time you've got frozen and boiling and liquid and frozen air tame. Okay, so that is the triple point. Now, again, different substances have different triple points, but it is it's a physical constant. It will not change because it will exactly happen at that temperature and at that pressure. Okay? So that's a little pub quiz question. It was amended, and I believe it was amended in about 1960. Up until then, it was very specially purified water at 1 atmosphere, but 1 atmosphere is difficult to obtain, as it varies from temperature to... In this classroom, the pressure is probably ebbing and flowing as it gets hot and cold, as the wind blows past the door. It's difficult to get a constant volume. Okay? Very quickly, we will talk about Daniel Gabriel Fahrenheit, a German dude who was different. He was a bit weird. He placed his thermometer in the human body and he said, I'm going to call that 100 degrees. He then took ammonium chloride, which is a white salt, and he's got a saturated solution of ammonium chloride in water. And he kept stirring until he could get the coldest possible temperature on his glass thermometer, and he put a notch there and called that 0 Fahrenheit, which came out to be about minus 32 degrees. If you've done lower school science and you've stirred salt in water, some of you may have gotten down to minus 10 degrees with sodium chloride or ammonium phosphate or something. But he managed to get it down to 32. So that's bad. I mean, clearly he called it 96, which is 2 to the 6th power, lost or exaggerated. It's stupid. I mean, body temperature can change depending on a lot of factors. So, yeah, you should not have a temperature scale with the endpoints are based on things that could change depending on whether it's hot or cold, or you've got a fever, or you've just been out playing sport. It's a stupid idea to have those endpoints. The conversion is not that. The conversion is degrees Fahrenheit equals degrees Celsius times 1.8, or it's sometimes referred to 9/5 plus 32. Okay? What's frozen? Thanks.
Yeah.
Oh, there you go. It is just a tedious task. It's just tedious, busy work if we ask you to convert to Fahrenheit, because no one uses it except for Americans. They're stubborn. Any Americans in the house? You go. But I thought I'd show you that other people in different countries were doing different things. This is how the metric and imperial kind of managed to stick, because countries and regions of the world sort of said, yeah, we're going to keep using this, and for 50 years they're developing their scale, and then on the other side of the country, other people are developing their scale, and then when science tries to sort of amalgamate in the late 1700s, early 1800s, they sort of said, well, SI units, yeah, we've got to make sure we've got everything, everyone's singing off the same hymn sheet. So they got rid of Fahrenheit. Next. Lord William Baron Kelvin Kelson, the first English dude, British mathematician, physicist and engineer, did lots of things. He was rather clever. He figured out that there was a relationship, or it was known in chemistry that there was a relationship between pressure and temperature. You may have learnt that P1 over T1 is equal to P2 over T2. In fact, don't draw that there. Draw that over here. Yeah? Sorry about that. And if you're doing chemistry, you'll probably be learning P1 V1 on T1 equals P2 V2 on T2, and P1 V1 equals nRT. N is the number of moles, R is Rydberg's constant, T is temperature, but they're all absolute. Here's the problem. Using these ratios, a problem occurred if you went below zero. So obviously you can have a volume of gas where you're measuring its pressure and you heat it up and it's perfectly linear, such that P1 times T equals, well, yeah, perfectly linear. Yeah, because the ratio equals a constant. We could write here equals a constant. Equals a constant. But if you get into negative temperature, then your fraction then becomes negative and the ratio, the relationship breaks down. So what he needed was a linear scale. He did something really, really tricky, really ingenious. He took a gas, and down here on our temperature scale in degrees Celsius, so he used the Celsius scale. Let's say here is 0, and I'm just going to plot this in 200s. 200, 400, 600, 800, okay? And he varied the temperature of a gas and measured its pressure. And by knowing the ratio or the relationship, he got a linear relationship. That sort of curves away a little bit. Let's try again. Okay. Now, back in that time, I'm going to say late 1700s, early 1800s, they couldn't get much colder than 0 degrees, so they were all sort of in this positive temperature. But he said there has to be some limit, because have a think, what is pressure? Pressure is the force per unit area of your particle smacking into the walls of its container. The hotter the temperature, the higher the temperature, the more force it imparts to the walls of its container. That makes sense. You heat an object up, its pressure increases. If you cool it down, it's going to slow down. It's going to exert less momentum and impart less force to the walls of the container. If we follow that back, eventually there should be a temperature at which the particles exert 0 force, meaning they're literally not moving. It's a theoretical temperature at which there is no atomic movement of our particles. If you're not moving, then you can't smack into the walls of your container. So he extrapolated this data back by borrowing Mr. Hamdorff's ruler. He was able to extract... Wait, no, hang on. I've got this really cool... Oh, here we go. Watch me screw this up.
So am I a joke to you?
No.
I didn't get it.
Oh, look at that. Okay. Could you do so the same? And we will call this minus 273.149 degrees Celsius. This is known as absolute zero. Okay? Now, this is using, it's called an ideal gas. Sorry, people at the back. This is known as an ideal gas because obviously you have to ignore any condensing into a liquid and then solidifying into a solid. If you use liquid nitrogen, and eventually at some temperature it turns into a liquid, then into a solid, and then you're not going to get nice linear data. So we call it an ideal gas where we ignore phase changes. All right, it's a nice little trick. What was also cool is that it worked for any ideal gas. So you could get a different gas that might have a different pressure, temperature. You could just change the number of molecules, suddenly drop your pressure, and then you're going to get this. Now, hang on, can I cheat? Yes. What is Mr. Murray doing? You're going to get data that is also linear, and it will point to the same absolute limit. Okay? Obviously, the greater the range of temperatures you can produce, the more confident and reliable your data is, a higher correlation to a linear equation. And he was taking many recordings of many temperatures and pressures of many different samples. And they were all pointing back to minus 273. Yes? But that's just a different sample. So here's involved, you've got basically a big metal sphere full of gas with a pressure valve or a pressure gauge, and then he just heats it up. So he's measuring temperature and pressure. Now, let out some atoms, and then let it cool down, do the experiment again. You're now going to have different sets of pressure and temperature points, but they all extrapolate back to the same x's.
We don't know.
Just a different sample. Different sample. Have a think. Less number of molecules would give less pressure because forces. You've got less particles smacking in. You're going to have less force per unit time. All right. Can I get rid of ruler? Yes, I can. This absolute limit is called absolute zero or zero. The Kelvin. No, that was right. Kelvin. I cannot spell. Or 0K. Capital K. Now, be careful. Every year I see students making the same mistake. Because Lord Baron William von Kelvin I, or whatever his name was, because he used Celsius in his experiment, he was actually measuring temperature in Celsius, it has the same scale step. Scale step meaning increase or decrease. So, an increase of 10 degrees Celsius, i.e. delta T equals plus 10 degrees Celsius, equals a delta T of plus 10 Kelvin. Okay? The change in temp is the same. It is not, and I'll give you an example that it is not. So 5 Kelvin does not equal 5 degrees Celsius. Okay? So you still get students that a temperature measurement can be converted between Celsius or Kelvin, but if we're dealing with the change in temperature, it doesn't matter what units they're in. A change in 5 Kelvin, up or down, is the same as a change in 5 degrees Celsius, up and down. So 0 Kelvin is minus, in the data sheet, unfortunately, this is why I don't like the data sheet, because they round everything to 3 sig fig. It's minus 273 degrees Celsius. But scientists have measured this to a lot more precision. The conversion, Kelvin equals degrees Celsius plus 273, and degrees Celsius equals Kelvin minus 273. Okay? Please note. No degrees. No. If I had 0 degrees Celsius, then my Kelvin is 0 plus 273. This classroom right now is about 20 degrees. So Kelvin, it would be 20 plus, we're in 293 Kelvin is the approximate temperature of this classroom. Okay? If we were at 10 Kelvin, then we're actually at 10 minus 27, we're at minus 263 degrees Celsius. This you are expected to be able to convert between. Okay? Again, let me just check the data sheet. I said it was in here. It's not. Why is it not? Oh. Well, we might have to give you that in a test. Homework. Can you get your homework diaries out, please? Why did I lose all of my pens? I set up all of my pens and pencils. Huh? Don't see you tomorrow, so do Monday. Good question.
I'll leave it to Monday to answer all.
The Pearson. So, yeah, sorry, the Pearson text, which Amelia has, and you can answer the question. Yep. So, Year 11, what you will find is I will place the questions in the booklets that I print out for you. Your textbooks can stay at home. All right? I'm not going to expect you to open up your Pearson science books. They can stay at home. Please read. The chapters are not long. Chapter 1.1 might be all of 3 pages. Alright? It is not long. Don't just rely on what I shout at you in 50 minutes. Read other people's thoughts on the topic, but I will expect you to answer all of these questions. I'll do attendance. Are we missing anyone? We've got 26. Hang on, let me just do attendance. Where are you going? Hang on, I've got to do attendance. Huh? Your parents have already been texted. I'm waiting. Hang on. See? Wilson. Alistair Parkinson's here. Everyone's here? Hang on. I'm waiting. It's not me. It's someone else. Do we have 26? Yes, we do. See you later, gentlemen. Amelia. Wait back. Georgie.